Alright, I'm recording this ahead of time because I won't be able to conduct the lecture today live for a few reasons. So the first thing we're going to go over is the homework assignment. The homework assignment that's due today called function calls. So let's go ahead and take a look at the assignment. And I'm going to put it into preview mode so I'm looking at what you guys will be seeing. Most of these questions are, well, they're multiple choice, which means you can just go ahead and find the answers. But the one that is a little bit harder is question number 11, because that's basically asking you to turn in the program. So let's go back to one of the previous slides where the program is listed. Okay. And I think it's the spacer where the program is listed. There we go. Nope. Alright, so I thought I had a main program somewhere, but I have to go find it. So this is just a general function call. And here we have the actual subroutine. So this is another example. And let's see, question number 4. There we go. So here's the C code, and this is the partial assembly code, just for main. So what I'm gonna do is let me go back to my command line interface, okay, and have it prepared. There we go. All right. So what I'm gonna do is I will copy and paste the C code so that we can look at the C code and the assembly code side by side. All right. So here is the C code, and then we'll also copy and paste the assembly code. Alright, so the assembly code only has main in it, but not swap, and your assignment is pretty much to implement the swap subroutine. So I'm almost done setting up everything here. Alright, so from now on we can just look at the command line interface, and I'll make this wider because I intend to show both the C code and the assembly code side by side. So making it wider makes it easier. There's more room to look at everything. So let's go ahead and open these two side by side. So swap.c is going to be on the left hand side. Swap.ttp ASM is going to be on, oh, okay, I used the wrong switch. It should be a uppercase O in order to go side by side. Alright, so I'm not going to go explain the main program, and instead I'll go straight into the swap subroutine. There we go. So what I normally do is I want to look at how things look like on the stack. So we know that PTR2 is pushed first, which means it has a higher address, and followed by PTR1, and then followed by the return address. These three items are pushed by the caller, and the callee can assume these things to be there. And then we have the local variable t. So what we want is to make sure that our stack pointer points to the local variable t when we are done setting up the stack. Now it is important to understand that the caller was set up to this point. Okay, so that means the callee, the subroutine, needs to do the allocation for the remaining one local variable, which only takes up 1 byte. So now we're going to use labels so that we can refer to the names as offset from where the stack pointer points to. So t is the lowest item on the stack, so it has an offset of 0 from where the stack pointer points to after we set up, after we allocate the space. The next item is the return address. Since we only have one single subroutine, it is okay to do it this way. Now we can also, kind of the usual thing that I do is to remember, how many local variables or how many bytes are used by local variables. So we can now say swap local var underscore size would be t1 plus. The t is referring to the offset to find t, and then the 1 is referring to the size of t itself. So when we add these two, we know the number of bytes that is used by all the local variables. And the next one up is ptr1. So ptr1 is return address 1 plus, and then ptr2 is ptr1 1 plus. There we go. So these would be the offset of items on the stack, but it doesn't mean that the stack would look like this, because remember, when the stack is all set up by the caller, the return address was the last item push on the stack. So that means the subroutine swap is responsible to push or reserve space for its own local variable t. So we're gonna do it over here. So we have a LDIA with swap underscore local var size, and then we add this much to the stack pointer, or excuse me, we subtract this much from the stack pointer, because to allocate is to subtract and then to deallocate is to add. It is a little bit counterintuitive, but that's kind of the way that it works out. So to get out of the subroutine, we have to do the reverse, so that we deallocate local variable t before we get to the usual return code, which is ld bd. Now this time, because swap is a void function, I could have used variables, registers a, b, or c, but since we have been using register b for a long time, and using register b cannot be wrong, because it is not used to return a value. So this always works. And then we want to increment d to deallocate the local variable, and then when everything is done, we use a JMPB, not a JMPIB, okay, because those two instructions are very different. So we use a JMPB to return to the caller. So at this point, if I were actually writing this program the first time as a student, I would test the program right now. I would just kind of run this through, even though the subroutine doesn't do a single thing. But I do want to make sure that it does return to main and everything looks okay when it returns. Okay. Now, since I'm not a student and my time is limited, so I'm not going to go through that trouble and assume this code is working. So now I go into the subroutine. The first thing I need to do is to retrieve whatever is pointed to by ptr1 as a parameter. So to do that, we have LDIA ptr1, which is, so now register A has the offset from where the stack pointer points to the local variable, the parameter ptr1, but it's just an offset. An offset is useless unless we add the stack pointer to it. So now A is an address. It is the address of the parameter itself. So the first LDAA will retrieve the parameter itself. So after this instruction, register A is going to be parameter ptr1, but we are not interested in ptr1, we're interested in what it points to. So that's why we need an additional LDAA to get to what ptr1 is pointing to. Now the right hand side is done. We will work with the left hand side. The left hand side looks about the same, except we have to use a different register because register A now has the right hand side value. So we use register B to compute the left value, or the L value. And it's about the same. Okay, we compute the address of T, except this time we do not have an LD instruction. We have an ST instruction, because register B now has the address of local variable T. So we just need to store the value of the right hand side, which is already in register A, into whatever B is pointing to. So that implements the first statement. The next statement is going to be about the same. Okay, so I'm not even going to bother to optimize the code. So this time we want to get to what ptr2 is pointing to. So now we have the address of ptr2, And now we have PTR2 itself. And now we have what PTR2 is pointing to. And then on the left hand side, this one is similar to the one before, but not exactly the same. So we have the offset to get to PTR1. We have the actual address of PTR1. And now we have PTR1 itself, okay, which is necessary. And then we store to whatever PTR1 is pointing to. And that's how we do the second statement. The third statement is going to be about the same, LDAT add AD. So now register A is the address of local variable T. And then we have one single LDAA. So the register A is now the content of local variable T. On the left hand side, we have LDIB PTR2, which is now the offset to get to PTR2 from where the stack pointer points to. And then we're going to have add BD, so the register B is now the address to PTR2. And then we have LDBB, so the register B is now the parameter PTR2. And finally, we have STBA, which is to store to where PTR2 is pointing to. So the key is to understand that we are not swapping the parameters, but to swap what the parameters are pointing to. So that should conclude everything, and we'll go ahead and give it a try. Okay, so we have cat swap.ttpsm to xclip-cell clip. And now we switch to the assembler, but I can't really show you guys, this code because some of you are still working on it. So I'm gonna have to make a new assembler, and we'll call this secret assembler. And the secret assembler cannot be in the shared folder either because everybody can see what is in the shared folder. So I need to move it around to some place that is not shared. Alright, so when I get up to here, we'll go to things that are specific to this semester, and we'll just kind of move it here. Alright. Alright, so at this point, it really should not be shared. Let me just click on share and see what it says. So right now it says, it's not shared with any particular person, restricted, only people added can open with this link, and I have not shared it with anyone, so that is correct. So now we go to source, paste the code into here, and just kind of make sure that everything looks good. I don't see any errors. Then we go to RAM file, download the CSV. Okay, and we'll put it into the temp folder, and we'll call this swap.csv. Now we have to run it on the command line. Now for debugging programs like this, it is very essential to be able to run it on the command line so that we can collect the trace data. Then we can run that data through the trace analyzer. So let me look for the previous command that has Java in it, and it's this particular one. So I'm going to copy it without the carriage return, so this way I can go back and just change a few things. Yeah, I should have written the script to do this instead of just repeating a previous command, but I'm too lazy to do that. So now it's going to load swap.csv, which is the content of RAM. That's basically the output of the assembler. And then the output is, the trace raw data is collected in swap.tsv. Press the enter key. So everything looks good. And for the trace analyzer, I'm debating whether to make this secret or not. So I think I'm going to make this secret. Okay, so we'll go to File and make a copy. There we go. And I suppose when I make a copy, I could have moved it at that point. but I didn't. So now we have to move it. So we'll move it to, let's see, right here, move, and we'll put it into the same folder as the other one, which is in here. There we go. All right. So now that we have set up the trace analyzer, I would go to File, do an import, and upload the file, swap.tsv. And then we replaced current sheet, specify tab as a separator, and specify do not do any conversion. Now we go for import. And this is not too long. It shouldn't take too long to complete this whole thing. So here's a summary. The whole thing only has 258 rows. So with this program, we need to know what are the two variables that are being swapped, what values are being swapped. So we have to look up the C code. In the C code, we can see that there's 3 and the 7, and basically the local variable of main should be swapped. So now we go back to the trace analyzer, and we look for the writing of 3 and 7. So here's 1, 3 is at location FE, and then 7 is at location FF. So these two should be exchanged when this program is done. So I'm just going to go through a quick scan, and we can see right here FE is getting 07, and then FF is getting 03. So this is how we can validate that the program is indeed working. So that's it. That's it for the homework assignment and the key to it. And I will make the source code available at 7 o'clock, or sometime after that. But you already saw how I typed the program, so you can actually just copy the program and pause the video as you go along with the recording. All right. So what are we gonna do now? We got 2 more classes. Today is one, and the next Tuesday is the other one. Next Thursday is going to be a review for the final exam, which is going to be on the 17th of December. So once again, the final exam is on the 17th of December. I will send out the form so that you guys can mark what time slot you will not be available to take the final exam. So we are moving on. Okay, so we are moving on to the next lab. I will assign it today, and you have 1 week to finish it. So the next assignment is the recursive Fibonacci sequence thing. So this is going to be the next homework assignment, and I will release it now. It does have a key of fib. FIB is the key of this particular lab, and it's going to be due on the 10th. So December 10th, 7 p.m. December 10th, 7 p.m. All right. And then save and publish. And there we go. So this is your last homework assignment, which is the recursive call. All right. So what we'll do today is I'm going to show you maybe 2 programs that can help you with this particular homework assignment, and how you would use the content of these 2 sample programs is up to you. So I'm not going to point out, okay, you can borrow this element from this program and that element from that program, and when you combine all of these, the program is going to work. Nope, I'm not going to tell you that. Instead, I'll give you 2 programs, and individually each one will illustrate one particular aspect of the program that you need to write, but you kind of have to look at combine the 2 of them in order to write the program that you need to write tonight for next week. All right. So the first one, I'm just going to say sum, okay? And we'll start with the C code first, and you work on the assembly code, on the side. In fact, I think it's probably best if I use online GDB. Okay, so this way, I don't need to run it on the side. And we'll go ahead and include stdint.h, standard integer.h. And here is my subroutine. Okay, it's uint 8 underscore t, unsigned 8-bit integer. And the subroutine's name is just going to be sum, and it has one single parameter, which I will just call x in this case. And in this case, I'm going to return, and use a ternary operator to specify what I'm returning. If x equals to 0, then I will just go ahead and return a 0. Otherwise, I will return x plus the summation of x minus 1, or we call sum with x minus 1 as the parameter. So we'll go ahead and run this code a few times, just so that we know what it's going to do. Let's make it as straightforward as possible so we can do a straight transition to the assembly code. So in main, we have we have its own local variable, because I do want to illustrate what happens when you have two names, belonging to two different subroutines. They're both x. What are we going to do in this case? So I do want to illustrate that. So x is going to be some. So for testing purposes, sum 0 is going to be helpful, because we want to make sure that when the parameter is 0, it simply returns a value of 0. So that's going to be useful. But we also want to test the recursion, so I'm going to use sum 3 in this case. So what this is going to do is it is going to, by the recursion ends, we have a 0, and then it goes back to add 1 to it, then it goes back and we add 2 to it, and then it goes back again and we add 3 to it. So the value returned and stored into the local variable x of main should be 0 plus 1 plus 2 plus 3, which is 6. So so this is what I think the program should do. It doesn't mean that it's going to do it. Alright, so we should go ahead and debug the program first, just to make sure that this program works the way it's supposed to. So we put a breakpoint on line 21. Click debug. Okay, I forgot about something. In function sum, I forgot the semicolon at the end of the statement. Alright, let's try that one more time. Alright, so this time it does work, or it at least compiled. We run the program, we get to the breakpoint, we print the value of x, it is indeed 6. Alright, so the program works the way it's supposed to. And then the next thing we will do is to copy this into the command line interface. So this way I can write the code side by side. So we Control C and then switch to the command line and copy whatever is in the clipboard to sum.c. Oh, okay, that won't work. Alright. Let's try that one more time. Cat to sum.c and Control Shift. There we go. Now we can paste. Control D and the pasting. And then we'll use the editor to look at the C code on one side and the assembly code on the other side. Alright, C code on one side, assembly code on the other side. We start with a no op, typical thing. And we'll just go ahead and put main here, okay, just for simplicity, okay. Sub dd to initialize the stack pointer, because the stack pointer should be 0, because it is 1 byte past the end of the memory space. And also in this case, we have a local variable main. So in this case, because we have local variable x in main, and we also have parameter x of sum, so I'm going to use main underscore x to for the local variable in main. and then we have main local var size being main x1 plus. So that takes care of the declaration of the labels. And then what we'll do is do the usual LDIA with main local var size, subtract that much from the stack pointer. And then when everything is done, we'll go ahead and do the opposite. And subtract dd needs to be before this, because it's kind of like the initialization. We'll do it before main. There we go. And then these two lines need to be copy pasted and modified before we get to the halt instruction, because we allocate and then we have to remember to deallocate for the local variable x. So now we have to call sum with a parameter of 3. So LDIA3, decrement d, stda, that should push 3 on the stack. Then we have LDIA dot 6 plus, decrement d, stda, jmpi to the name of the subroutine, which is sum. So that should call the subroutine. When we come back from the subroutine, we have to make sure that we remove the parameter, which is still on the argument, which is still sitting on the stack. So we have an increment d to take care of that. Now I keep talking and not typing. I'm not putting in the comment because I want you to do that. Okay? Because I want you to put in the comments as you kind of go through this recording and have your own understanding of the material. So after this, we have the result or the value, the return value is stored in register A, and we need to store that into local variable x of main at this point. So we have LDIA. Cannot use A because remember register A is the return value from the subroutine, so we have to use a different register. So we can use register B or C, either one is going to be okay. So I'm going to use register B in this case. Main underscore x, add BD, so that B is now the address to the local variable x. And all we need is a ST instruction to store whatever is in A, which is the return value from sum, to store to where register B is pointing to. Register B has the address of x at this point. Alright, so this is main, and now we can go ahead and write sum. So sum starts like this. It has one single parameter, so just for just so that I know what it's going to look like, we have x, we have return address on the stack, and nothing else. Okay, so that's all we have on the stack. They're both supplied by the caller, and since we do not have any local variables, I'm not going to bother with the allocation and deallocation. It doesn't really hurt if you want to say, sum underscore local var underscore size is 0 and just go do the usual thing to allocate and deallocate. That's perfectly okay, except, it's really kind of a waste of instructions, so I'm not going to do that here. Alright, so what we need to do is now to define the labels. Sum underscore x is a label, and then sum return address is also a label. Because the return address is below, it is at the lowest point of the call frame, that's why it has a value of 0. And in sum x, the parameter is 1 byte on top of that, so it is sum return address 1 plus. So now we got the labels defined, and we are ready to perform the logic that is specified here. So before we can do anything, we have to load parameter x into a register so that we can compare that to 0. So we have LDIA sum x, okay, and then add AD, so that register A is now the address of the parameter. LDAA, because we want to compare the value of the parameter, not the address of the parameter, to 0. So instead of a compare, we can use the trick of using AND AA, and then we just check for the Z flag. Now, if this is not clear to you how this works, you have some material to review because we have talked about this technique already when we talked about the absolute value logic. Okay, and that was kind of a while back. So now we say JZI because there's no J and ZI. In other words, we cannot jump around. So JZI would basically go to a label that says return 0. So we'll call it sum return 0. And here we have the recursive call, and sum return 0 is a label defined here where we just have to, there's nothing to do because register A has the value of X already, and as a result, we'll just go ahead and go like, okay, fine, we'll just return that. So sum return 0 really has nothing to do because register A already has the right value before we get to the end of the subroutine to return, which reminds me, okay, I goofed because usually I would do that first. Retrieve the return address, deallocate the return address from the stack, and then JMPB to go back to where the caller wants us to go back. So the key is to go to specify what goes into the recursive call. So the recursive call is this part over here. There are several ways to do this because X is already in register A. So if I don't want to have to recompute X all the time, okay, we can just go ahead and say, okay, it is already in register A. But the problem is when you call a subroutine, even if it is recursive, you cannot assume registers A, B, or C can retain its content. So that is kind of the problem. And on top of that, even though we are pushing x minus 1, you cannot assume a parameter remains as is, okay? Especially in this case, because in this case, we did not have a const, for x, which means the subroutine is free to change the parameter itself. It really should be transparent to the caller. So the proper way to do this is, in order to save the value of x, is to push it on the stack. So we have decrement d, stda. So what I'm doing is I'm pushing the value of x on the stack, and then I can go ahead and decrement a. Decrement a will give me x minus 1, and then I push that on the stack as an argument this time. So now we push it as an argument so that we are ready to call sum. And now we need to call sum, which means we have to push the return address. So we have LDI. We can reuse register A at this point because we're done with what we need. We're done with having to know the value of parameter x. So now we can go ahead and LDIA with .6 plus decrement D stda. So now we have pushed the return address on the stack, and then JMPI to sum. Yes, so recursively calling a subroutine is no different from calling any other subroutine. We go through exactly the same motion to call. When we come back, we have one byte of argument sitting on the stack, and we have to remember to deallocate it. So increment D is deallocating that particular argument from the stack. So now the stack should be balanced, which means the stack pointer should be pointing back to x, which is kind of buffered and stored on the stack. So to retrieve that, I can use a LD instruction, but I don't want to LD into register A because register A now has the return value of the recursive call of sum. So I'm going to retrieve it into register B, and then I increment D to deallocate the saved x, which was sitting on the stack. So at this point, register B has x, register A has the return value of sum x minus 1. So all we need to do is to add those two. So there are two ways to add. You can add AB or you can add BA. But add AB makes more sense because register A is supposed to be the register specifying the return value. So add AB, is adding B to A, which means, we got everything that we need, in register A. if I had used add BA, then I have to copy register B back to register A. It is doable, but it's wasting one extra instruction for no particular reason. So we are pretty much done. Okay. So next is for me to test the program. Now, frankly, I really hope this program is not working. Okay, so I can illustrate how to debug a program like this. Um, so we'll see. So we have test sum.ttpsm to xclip dash cell clip, and then I go back to my secret assembler and go to the source tab, paste the program in, and I think this program is probably shorter than the swap subroutine, so I'm gonna have to clear out a few rows down here, because otherwise we have undefined labels. So get rid of those, and everything should be good now. Oh, okay, guess not. Alright, so what did I do? There we go. It says unrecognized something in RP and in reverse Polish notation. Alright, so let's see. I think I used a comma instead of a dot. Yep, that looks like it. Alright, so let's change it to a dot. Now everything is good. We go to RAM file, and then we just download it back. And this time we'll call this sum.csv. Alright, so sum.csv, save. Alright. And then we go back to the command line and run the whole thing again. Okay, so this time we go back here, and all we have to do is to change the swap to sum, like so. And it does the job. And now we go to the secret trace analyzer so that we can upload the new trace. So we import, upload, and specify sum.tsv. My cat is reminding me that it's dinner time. And it is, and it really is. Okay, well, it's almost 5 o'clock. Alright, so we specify all of these options, click on import, and then we wait until the progress bar is done. Okay, this is not a pretty long trace, so it should be, it should not be too hard. And then we get to summary, find out how many rows we have, 442. Okay, well, that's not too bad. And we just go to row 442. And so there are a few questions. What are we looking for? The first thing is the stack pointer should be back to 0, 0. Okay, so so it is the case. So the stack is balanced, and we do end up with the halt instruction at location 17. That is good as well. But we also want to make sure that 6 is stored to local variable x of main, which is at location FF. So we are looking back, and we can see that 6 is indeed stored in location FF. So I have confirmation that this program is working. But how we use the stack, that is the story of what these 400 lines or rows in the spreadsheet are trying to tell you. So if you don't know exactly how this program works, I would encourage you to go through the trace analyzer and basically find out how this works, because the execution of the program is really just kind of following whatever is in the source code. And the trace analyzer has column A telling you where we are looking at, or what instruction, which instruction we're executing. So that should give you a complete picture of what is going on the stack. Now on the side, what you probably want to do is to utilize some drawing so that you can kind of keep track of what is on the stack. The difficult part of using a piece of paper to draw that stuff is For this program, not so much, okay? But for Fibonacci, it is an issue because we overwrite locations in RAM over time. So if you use a piece of paper, it may not be the best medium to do it. You can use a spreadsheet because a spreadsheet is basically a table, and it's very easy to copy and paste. So that way you can basically just copy and paste and go like, okay, after this instruction, the stack is going to look like this, okay? And that makes it kind of easier to kind of keep track of what the stack looks like at a particular time. All right, so I'm pretty much done with the first sample program. Moving on to the second sample program. So the second program, I'm going to go to online GDB again, and the second sample program is actually in a way simpler, and in a way it's slightly more complicated. Okay. So what we'll do is we define two subroutines, and the first one is named Johnny. You'll see why it is called Johnny, because it specifies a value of 5. Okay, Johnny 5. Yeah, I know I'm dating myself, because that's a pretty old movie. Johnny 5 is alive. The next one is gonna be Ryan. Okay, because Jerry Ryan is the name of the actress who plays 7 of 9. And this particular subroutine returns 7. Okay. In the main program, we still have local variable x, but this time it is going to be storing the sum of Johnny and the return value of Ryan. So we have the return value of Johnny, and then we have the return value of Ryan, and we add those two in order to store the value into x. So that's what we're going to do here. All right. So not surprisingly, okay, if we end up on line, when we end up on line 25, x should have the value of 12, because 5 coming back from Johnny plus 7, which is coming back from Ryan, is 12. 5 plus 7 is 12. So let's not take any chances, just in case I goofed up. Let's go ahead and run the program and print x, and indeed x has a value of 12. Very good. So now we'll go ahead and copy and paste this program onto the command line, because I want to show you the C code on one side and the assembly code on the other side. So we are copying and we paste it to how should we call this? Bots is good. Well, I mean, 7 of 9 is technically not a robot. She's a Borg, which is a cybernetically enhanced human. But we'll just say bot. I don't think anyone's going to complain. The Borg does not have a union to complain about stuff like this. Alright, so we look at bots on one side, and then we look at bots.ttpsm on the other side. There we go. Alright, so we have no up, sub dd to initialize the stack pointer, main first. Indeed, we can recycle most of the stuff that we have in the other program, so I'm going to do that because there's no need to repeat what we have done already. Oh, okay. Sum.ttpasm, I misspelled. Alright, so we're going to copy the first 4 lines, or we can copy everything and then decide to, and then we can delete stuff that we don't need. So we are on line 3, and we'll copy up to line 26. And okay, we have to go back to bots.ttpasm, paste, okay, and we can delete everything in between. So that's from line 10 to line 22. There we go. All right. So the first thing we need to do is to call the subroutines. Addition is commutative, which means you can do it in any order we want. But because most people read the program from left to right, so I'm going to call Johnny first, and then we'll call Ryan. So at this point, I think you should probably know that calling a subroutine involves saving the return address on the stack, right? Because we don't have any arguments to push this time. So this is going to push the return address on the stack, and then we use a JMPI to continue execution at Johnny. When it comes back, there's nothing to clean up because we don't have any arguments, so there's nothing to clean up. Then we have to call again to Ryan. So we basically have the same kind of instructions, except this time we are JMP jumping to Ryan instead of Johnny. So these two are function calls, but the problem is register A, right coming right back here, has the return value from calling Johnny. But this is going to erase it, right? So some people will go like, well, if I change this to register B, then everything is going to be good. No, everything is not going to be good because Ryan is also going to specify its own return value in register A, so it's not going to be okay. Then some people is going to say, well, but we can copy that to register C, right? We can do a CPRCA, and then from here, we're good. The way I implement this program, the answer is yes. But there's no guarantee. Okay, the problem is there's no guarantee that the subroutine will not change register C. So you cannot make that assumption. And as a result, even though this technique would have worked in this case, from the sense that the program would give me the correct answer, it is the wrong approach. Okay, so in the final exam, okay, even if a program quote unquote works, in other words, it end up with the same final effect as the C code, but if the approach is wrong, I would take points off because the point of this class is to understand how to get it to work in all cases, not only in some cases. All right. So what are we gonna do? We need to save the return value of calling Johnny, and then add that to the return value of calling Ryan. So the best place to put something, to save something, is on the stack. So what we can do here is to say, hey, at this point, we have the return value of calling Johnny in register A. Why don't we push it on the stack? All right, so we are pushing the content of register A on the stack. And after this, I can freely reuse register A for whatever I want because it is already saved on the stack, and that is, that's a pretty safe location. So by the time we get to here, we have the two return values. The return value of Johnny is sitting on the stack because we pushed it earlier. The return value of calling Ryan is actually in register A. So what we need to do now is to retrieve the saved return value of Johnny from the stack first. So that's an LD instruction, and I cannot use register A again. We have to use register B because register A still has the return value coming from Ryan, so we can't use the LD and specify register A to receive the value. And then we have an increment D to deallocate that locate that byte on the stack. So now we are finally ready to add the two return values. The return value of Johnny is in register B. The return value of calling Ryan is in register A. So I'm just going to add B to A because register A is also going to be okay. In this case, it's not important because we are not specifying a return value. So it's not as important. I could have used add BA. That's fine too. But we have to remember to store this in local variable x of main. So now we have that code. We just load LDI main x, add BD, So now register B is the address of local variable x of main, and now we can store like that, and then it should be done. Okay. Now let's go ahead and test this program. And to do that, we are gonna cat bots.ttpasm and pipe it to xclip cell clip. There we go. And then we go to the secret assembler. Secret assembler is right here. Go to the source. And if I just want to kind of nuke everything in column A, this is one quick way to do it. And then we paste the program which is in the clipboard right now. And then we just have to check. Oh, okay, I forgot to implement the 2 subroutines. Duh. Okay. Alright, so back to the drawing board. Because I have not yet implemented Johnny and Ryan. They're really simple, but the program also won't work without them. So we have Johnny first. Okay, so Johnny. We want to return the value of 5. LDI A5 is going to work. And then we have the sequence to return from a subroutine. So we have LD BD to retrieve the return address, increment D to deallocate the space used by that return address, which should not be on the stack anymore because we have already used it, and then JMPB to continue execution in the caller. So lazy me is going to copy and paste and change this to Ryan to return 7. There we go. Oops, 7. There we go. Alright, so now we do the whole thing again and paste it into my secret assembler. And this time there's no complaints whatsoever from the assembler. Excellent. We go to the RAM file and then we download it. We download the RAM content. Basically, that's the object code that's going to run in the simulator. And we'll call this one, I don't know. Bots, right? Yeah, bots.csv. And then we will run it on the command line. There we go. So we just change a few things, like so. Press the enter key. It's done. Then we go to the secret trace analyzer. Go to sheet 1. Re-import the TSV file. Okay. Like so. And then specify bots.tsv. So if this process is kind of new to you because you have not yet used this to debug your own programs, you probably want to start using it. Okay, because the final exam probably this will be useful in the final exam. Okay, so we import the data and give it a little bit of time to analyze. Alright, so we go to summary. We only have 152 rows this time. And what we're looking for is storing a 12 at location FF. But the 12 is known as 0C in hexadecimal. So that's what we're looking for, and we got it. Okay. So what I have done is really just to verify that the program works. Okay. As I wrote the program, I explained how the program is supposed to work. But when the program actually runs, okay, you kind of need to go through the stack, go through the trace analyzer, and find out how we pushed something on the stack, which is the return value of Johnny, and then later on retrieve that after we return from calling Ryan, so that we can add the return values of the two. So that is something that I want you to do. Okay, so at 7 o'clock I'm gonna make everything available, which includes the video itself. and also the C code and assembly code of swap, sum, and also this one, which is the bots. Okay, so there are three programs that I'm going to include in a package, and I will get all of those uploaded at 7 o'clock. Okay, um, I will be around at 7 o'clock. It's just that, I won't be able to stand or sit in front of a computer for any extended amount of time, and that's why I have everything kind of pre-recorded, but I will still be able to check my messages on Discord, starting at 7 o'clock. All right, so I think that is it. Well, sort of. Let me check how long this recording is at this point, and because I cannot remember when I started recording, and it doesn't tell me about when. Okay, fine, we'll figure out. Okay, so I'm gonna look at 2020 12:03. Oh, okay, it doesn't tell me quite how long it has been at this point. Oh, but it does tell me when it started. So the start time is 4:18, so I still have a little bit of time to go. I basically have another 20 minutes to go. Cool. That gives me something to do, right? So with the Fibonacci program, it is a double recursion, which means we have to go for one recursion and then we have to go for the other recursion. There are other algorithms like that, and the Tower of Hanoi is one of those. So with that, let me use my tablet so that I can show you what it is supposed to look like. And let's see. Let me see if that thing is still running. Nope. Okay, now it runs. Oh, because my tablet is off, so it does not work like that. Alright, so let's give it one more try. There we go. Oh, okay, there's another process running and I need to kill it first. Alright. Oh, okay. Alright, so no. Oh, okay, it is running. Well, if it's running, I should be able to capture the screen. Let me check. Yep, okay, very good. There we go. Alright, so the Tower of Hanoi is an interesting problem. You have three posts, okay, so I'm going to post. Okay, so we have post. I'm just going to label these as post A, post B, and post C. So the idea is we have some disks, okay, the largest one is always at the bottom, and as it goes up, they get smaller. So the idea is we want to move all the disks from post A to post C. Then you go like, that's pretty easy. We just have to take this stack of 4, lift everything up, drop it into post C, and we are done. Well, okay, so the first restriction is we can only move one disk at a time. Okay, I'm going to write it on the side. Move only one disk at a time. Okay. And we also want it to look like exactly like this, after everything's moved to post C, which means the largest one should be at the bottom, the smallest one should be at the top. Okay. So some people go like, oh, that's pretty easy. We move the first one from A to B, then the second one also to B, the third one also to B, then fourth one also to B, and then we move the largest one, which is now sitting on the top in post B, to as the lowest one in post C, and then we keep moving it, and everything should be done. Okay, so there's one more restriction. This is the first restriction. Second restriction is smaller disks must be on top. All right. So now it gets a little bit complicated, right? Because we go like, oh, how are we going to do this, right? Because we can only there are two restrictions. We can only move one disk at a time, and on top of that, a smaller disk, can only be on top of a larger disk. So it sounds like a pretty big problem. And this is why recursion is useful, okay? Because we can say, we'll just kind of say that magically we can move these three first, okay? So we'll move these three to here. Then, so I'm just going to make a picture here. This is the first step. And then once we have a configuration like that, then we move the bottom disk all the way to where it's supposed to go, the destination. This is step 2. And then we move the stack of the smaller disks from post B to post C. So that's the third step right there. Then go like, but Tech, aren't you assuming a little bit too much that we know how to move the 3 disks from post A to post B? And then I go like, well, is it too much of a problem? Because after all, the original problem is to move 4 disks, right? So I'm making the assumption that the same thing would also work on 3 disks. And this is how we use recursion. Okay, this is how we use recursion, or in this case, proof by induction. Is the same idea. All right. So what parameters are we looking at here? So when we need to call the Tower of Hanoi, we need to supply a few parameters. The first parameter is where are we coming from, which in the original problem is post A, and which post is the via. Okay, in this case it is post B, and where are we moving these things to? And that would be post C. Oh, I forgot one thing, so let's get rid of that. And the question is how many disks need to be moved from the from post using the via post to the to post. Okay, so we have an and over here. So now the question is, okay, what do we do? All right, so let's turn this into a subroutine. We start with a void, okay, because it doesn't actually return a value. So we just have to go back to the picture. Okay, so the picture says the first step is to move all except for one disk from the original from post to the via post. Okay, all right, so let's do a recursive call, Hanoi, and we are moving from the from post, but now we have a problem because we want to move from the from post to the via post, but it needs its own via. So we will say, we'll use the to post as the via in this case. And the number of disks that we want to move is going to be n minus 1. So this is what step 1 is about. Okay, step 1 is just this recursive call. And then step 2 is moving the largest disk at the bottom all the way from the from post to the to post, like directly, because it's just one single disk. So the step 2 is, quote unquote, okay, I will put it in comments here because we don't have a robotic arm. There's no actual moving. So there's really nothing that I can display when we are working with the toy processor. So in this case, I mean, there are a few ways to see this, to visualize it, but I'm not even going to bother. So we'll just go ahead and say move one disk from the from post to the to post. Okay, and that's not recursive because it's just one single disk. And then step 3 is going to move all the disks n minus 1 from the via post to the to post. But this time we're going to use the from post as the intermediate. So we have Hanoi, and this time we're moving from the via post using the from post as the intermediate to the to post. And there are n minus 1 to move as well. So this is the general logic, except this is an endless recursion because it doesn't stop, right? So we have to put everything in a conditional statement, which is if n is greater than 1, then we have this entire block of code. Else, well, the else is just this step here. So else is just a line of comment, which is the same as this comment over here. So let me do a lazy thing. I can do that with a tablet. Can't really quite do that with a with actual paper. Yes, that's my cat playing the piano. So we need a copy and paste. Okay, I'm just looking at the tool to try to find out which one is paste. Oh, right here. Okay, that's duplicate. And then tap any page with marker to paste. Okay, so we just click it here and move this thing to get to the right place. There we go. Alright, so now we are all done. Okay, close curly brace, switch back to the right tool. There we go. So that is the basic logic of Tower of Hanoi. And you can probably see that this step here can be a recursive call. It can be a recursive call to move just one single disk. So let me just give you the code in GDB first, okay? Because in GDB we can print stuff, right? So that can be handy. Alright, so let's go ahead and implement that code here. I'm just looking at the time to make sure that I got enough time to do this. Alright, so we have void Hanoi, and then we have we just need 3 numbers, okay? 0, 1, 2, or 3 characters, A, B, and C, because they're really just identifiers of the 3 posts that we are allowed to use. So we'll just go ahead and use, I don't know, unsigned for this, okay? Unsigned from, unsigned via, unsigned to, and an unsigned n. So now we got all the parameters specified, and then we specify the logic. So we check to make sure that n is greater than 1 when we perform the recursion. Otherwise, okay, I really do not like the fact that it has, it automatically complete the end curly brace, because normally I do not like to type like that, and I have to adjust my habit to do it. Alright, so the recursive call is from Hanoi. We are moving from using the to as the via and using the via as the destination, n minus 1 disks this time. And then we moved one single disk from the from post using the via post to the to post. Now the via post is really not going to be used because we only got one disk to move this time. And then we move everything from the via post using the from post as the via this time, and the destination is the to post, and there will be n minus 1 of those. So that specifies the recursive case. And then for the non-recursive case, assuming that n is at least 1, we can go ahead and use a printf here, okay, which is basically just for the output. So we can now say move disk 1. Okay, we'll focus on just 1, okay, because every single move is only moving one disk. So we move one disk from %u, which is a placeholder for an unsigned number. I should say post %u to post %u. So we basically specify from which post to which post, and then \n as the line feed character to so that we terminate the line. And then we specify, the from and the to. There we go. And that should be it. All right. So put a semicolon here. And then in the main program, all we have to do is to call Hanoi with some parameters. Okay. So we'll go ahead and start with something simple, which is 1. Okay. We also have to label the posts. So we have posts, 0, 1, 2. Instead of A, B, and C, the posts are numbered from 0 to 2. And we only want to move, and there's only one disk to move, okay, which is 1 here. And we'll just go ahead and test this program, see how it works. So we go to debug, run the program, and it basically says, oh, we still have that stupid breakpoint. Okay, we'll continue execution. And it says move one disk from post 0 to post 2. Now that is correct, okay, because we only got one disk. So now let's go to the program. Stop the program first. And then this time we change to 2 disks, okay? What if we have 2 disks? What are we going to do? And then let me see what happens when I just click run, okay? There we go. So now we want to look at the output of this program and see whether it makes sense or not. And what is this doing here? There we go. Alright, so it says move one disk from post 0 to post 1. That would be the smallest disk, the smaller because we only got 2 disks. And then it moved from 0 to post 2, which is the larger disk. And then it moved the smaller disk from post 1 to post 2 again. Okay. So to understand what the program is doing, let's go ahead and look at a new page using the whiteboard. Okay. So we'll clear this. So basically, this is what it looks like. Okay. These are the 2 disks. Okay, and these are the 3 posts. The 3 posts are labeled 0, 1, and 2. Step 1 is to move the smallest one, so we end up with this after the step 1. Because we moved this one to here. After step 2, we end up with this. The smaller disk is here, the larger disk is here. Because what happens is we are moving this one all the way to here. And then after the 3rd step, we have the desired output, which is the larger disk and the smaller disk at the destination. And to do that, this is what we are doing. We're moving the disk from the middle post to the right post. Okay. Oh, you can't see the bottom, but that's basically what we end up with. So these are the 3 moves. Okay, we have move 1, move 2, and move 3. And as far as the text output of the program is concerned, that's basically how it is represented. Okay, seems pretty simple, right? Let's try 3 disks and see what happens. So we have to press enter to exit the console. Now we can go back and edit the program. So let's go ahead and, oh, okay, it just pasted the wrong thing into this place. So now we want to try 3 disks and see what happens. So we go run the program again. And it is a longer output, not by a whole lot. Okay, you can see there are 7 moves this time. So if you are to play this out, you will see that it actually gets the job done. Can anyone guess what happens if I want to move 4 disks? It's going to be 15 moves, okay? And then the next one is going to be 31, and the next one is going to be 63, and so on. So what is the number? How many times do we have to call and return and call and return? Let's just say a lot, okay? It is actually exponential compared to the number of disks. If you got one disk, there's one move. If you got two disks, there are three moves. If you got, so the number is basically 2 to the power of n minus 1. Yep, that's a lot. And if you look up the Wikipedia entry on the Tower of Hanoi, it's really quite interesting because this originated as a problem at a temple where the monks are supposed to be moving the discs, and when the task is done, it will be the end of the world. So, and I think there are 64 discs if I remember correctly. So if you just look it up, you'll find it. Tower of Hanoi. And I think the Wikipedia entry has the story about that too. Alright, so let's just read this part. Alright, so you can see that it explains most things like if you have three disks, it will take 7 moves, and generally speaking is 2 to the power of n minus 1. But there should be a historical origin. There we go. And yes, so so I was actually correct. Originally, there are supposed to be 64 disks. So when the task is done, it'll be the end of the world. And as you can probably see here, assuming that we can move one disk per second, which is pretty fast, okay? It will take 585 billion years to finish, because that is 2 to the power of 64 minus 1 seconds. And then when you convert everything to years, it will still take 585 billion years. I do not believe the universe, this reality is going to last that long, because I think it's only measured in single-digit billion, possibly 2-digit billion, in terms of from the Big Bang or the origin of this world, of this existence, to today is at the most a double-digit number of billions of years. So 585 billions of years is a really long time. The sun is going to explode first, okay, to engulf the earth. And suppose the monk can be doing their disk moving thing in a shelter somewhere, so that they can keep doing it, okay? Because hey, the sun exploding is not really the end of the world. There are ways to survive it. Anyway, let me check again, because I cannot remember when this recording started. So I'm just gonna check in again on the side. And alright, so I started at 4:18. So technically I owe you 1 minute. Nope. Oh yeah, I still owe you like 50 seconds. So so now the question is, okay, given that this is the C code, how would you do it in assembly? This is actually not much harder, okay, if any, compared to the Fibonacci homework assignment, because it looks like there are 3 recursions, but we know that the middle one is not really recursive itself because we're only moving one disk. So it really is the same thing as Fibonacci, where we have one recursive call that can go really deep, and then we have another recursive call that can go really deep. So this can indeed be done using the TTP ASM. The only limitation is we have a very small stack. So and then we got 4 parameters to push on the stack. So if you think about it, there are 4 parameters on the stack plus the return address. So every single call is going to consume 5 bytes on the stack. And there really not a whole lot of space left, after we perform the logic and also the call and the return and stuff like that. So that really kind of limits, how big of an n we can specify. In theory, but the speed of doing this is so slow that by the time you get past, I don't know, let's try 5, as n, there won't be, you won't have the patience to wait until it's done. But in theory, yes, it can be done. The only thing we cannot do using the toy processor is to print out something. We just don't have any means to do that with the current TTPSM. So the else statement can remain basically empty, because there's really nothing to do. But other than that, everything else can be done using the toy processor. So when you're done with the homework assignment, the Fibonacci homework assignment, and you feel that I'm bored, I want to do something else, try this one. Okay, it's kind of interesting and kind of, it's fun to do. Um, so what I'll do is I'm also going to say that structures will not be in the final exam because I can't, there's not enough time to give you a homework assignment on the structures. So on Tuesday, next Tuesday, I will continue to talk about structures, but it will not be on the final exam. So you just kind of need to understand the concept, but it won't be there won't be any assessment based on structures in the final exam. And that's it. So I hope you guys will have a nice weekend. I'll see you on Tuesday, and at 7 o'clock, this stuff will be visible to you. And that's it. All right. See you next Tuesday.